restart because we have to finish before 10 minutes before the hour, so we better restart. And we have to actually, in any case, we know the problem that we are going to solve now is this problem, So first question you have to ask yourself is, what is the UTP here and what is the LTP here? It's the same value, one is positive, one is negative. So you have your hysteresis is 3 volts. How much is UTP?
1.5 volts.
1.5 volts. And LTP?
Negative 1.5.
Minus 1.5 volts. So always remember that the LTP and UTP is half of it. Sometimes in the final exam, the students just uses this one directly instead of this to calculate the resistances. Okay. So then you want here, basically you want 1.5 volts here, isn't it? You want 1.5 volts here. Okay, and you can take it when you are positive, you take it from V set plus. When you are negative, you take it from V set minus. So how much is V set plus? 12.8. 12.6. Okay, this is 12.6. This is minus 12.6. Okay, so you can have two equations. 1.5 volts equals R2 divided by R1 plus R2 into 12.6 volts, also minus 1.5 volts equals R2 by R1 plus R2 into minus 12.5 volts, 12.6 volts. So it doesn't really matter which equation you use, either one is fine, and you just have to do one of it. Sometimes the students does two of them. The student will do this and also will this, but you need to do one only. Okay, because the amount of the upper and lower trigger point, the magnitude is the same, so you need to use only one of them. So you can arbitrarily, like you did last time for a voltage reference, you determined what was the R1 and R2. So here you are going to determine the R1 and R2 for the required amount of hysteresis. Okay, so have you finished it, or maybe you can start it now and give me an answer in 10 minutes time, 5 to 10 minutes time. It shouldn't take that long. You got already your answer? Okay, everybody got the answer? So I would like everybody to solve it now, on paper and pencil. Okay, paper and pen. So who wants to solve this problem here? Who wants to solve it? Then we will do something else. They like you. I guess so. So what was the name again?
Jay.
Yeah. Okay. Thank you.
Thank you very much.
Thank you. Okay. So J got the correct answer, which many of you I have seen got the same answer, because you pick one of them as 10 kilo ohm the other came out to be 74 kilo ohm, and this is fine. So you just, if you have such a problem to solve in the exam, just be simply just check what, if a 3 volt is hysteresis, then it will be half of it, and then you can use either of the equations and choose a value which is not too large and not too small. And that's the story about this comparator with hysteresis. So we'll now close this chapter. You can go at home and practice some more if you like by changing. You can change this voltage, okay? Change your tripping point, and you create many problems for yourself, and then solve them. If you just solve 2-3 of them, that's good enough. It's not very difficult, isn't it? Okay. So we have then covered everything that we want to know and discuss on comparator in this course. You see, we don't call paper anymore. Do you know that? We call every paper a course. Okay. So this is a course, not a paper. And the course have run the course on. We have ended our course on comparator. So please write it down if you want to, and I'm going to now erase all of this. End of the story. Okay, so I'm going to erase this. Can I erase this? Okay, I'm going to erase all of this.
I know, it's just I wanted to. I don't like
We can use a op amp to create negative impedance. This pen is also ran out of ink. Negative impedance converter. Okay, how can you use a op amp to produce a negative impedance from a positive impedance? You won't actually have a feeling about the implication of it or use of it at this moment and at this level, but at a later stage, when you study oscillators or other kind of more advanced electronic components, then you'll understand the importance of negative resistance or negative impedance. Okay, so here I'm just going to go through a basic discussion on negative impedance converter using an op amp. So if you have an op amp like this, okay, and Z here. So Z is your impedance, which we will try to convert into a minus Z. Okay, and you have two resistances of equal value feeding back from the output. This we call it R, and this is of equal value. We also call this R. And we have input here, and we apply a source here. And looking into this terminal, we have an I input current. I. Okay. And also, we have this Z connected here to ground from the inverting terminal, and if you apply a voltage here and looking into this terminal where a current is flowing, you can also define it as a Z in, which is equal to V in divided by Z. Correct? If you anytime you have a voltage source and is driving a current, then the ratio of the voltage with the current is your input impedance. Okay, you have a voltage, it's driving a current. Take the ratio of the voltage with the current, that is a impedance looking here, looking into that terminal. Okay, so how this actually converts this Z into negative Z? What we will now say is that Z in is equal to minus Z. So if you apply a Z here, then with this configuration, if you look in here, you will get a minus Z. We want to show it, expression how actually this could happen. So V in minus V out. Okay. Sorry, I in. What is the current I in? I in is what? This current. So this is the op-amp. Is there any current flowing here? No current. So the only current flowing is this way. Okay. So this is I in. This is also I in. Okay. Then I in is equal to, this is your V out. I in is equal to V in, because the direction is this way, so this must be higher potential. V in minus V out divided by R. Okay. This is your I in. And what is your Z in? V in over I in. Okay. This is Z in. So I in you have got here, so we can label the equation as 1, this as equation 2, then Z in is equal to V in divided by I in equal to V in minus V out divided by R. We call this equation 3. So I will let you absorb this before I will write some more equations. So are you happy with these equations? These 3 of them? Make sense? These 3 equations, are you happy with them? Okay. So now we will go into, just make it, organize this a bit more. So we will write that Z in is equal to R into V in divided by V in minus V out. So if you want to write Z in terms of impedances, what you want to do is that cancel V in for the top and bottom, For this, if you can write V out in terms of V in, that would help. Okay. So can we write V out? What is the relation between V in and V out? So this is V in. This is V in here. What is the voltage here? V in also, exactly. Close to V in. We don't say V in exactly, but it's essentially virtual V in. Okay, that's also V in. Then from here you see what is V in. So this we will call equation 3, this we will call equation 4. And here we will create another equation which gives you the relation between V in and V out. Okay, and V in equal to what? V in equal to what? Who can do this for me? This is very easy. Who can find out the V in and V out relation here? It's just based on what we have done. Who can do it? John has already done for today. Who wants to do it from there? Yeah, what was the name again? Russell? Sure. I mean, if you could give your own just it would help. It's very easy. You see, what you did before is just extension of that knowledge. You had R1 and R2, remember? And you did a voltage divider. This is the same voltage divider where you have R and another one is a Z. Both are ohms. You see, Z is the impedance which is complex. It has got a R and a L or a C. But this is also ohm, this is also ohm. It doesn't do anything. It doesn't bite you. No. These are harmless creatures. You know. So the way you treated R1 and R2, you can treat Z as R2 and R1. You know. And just write the voltage divider equation. So V in is the voltage division of V out by R and Z. There's no R1, there's R. Okay, then there's a little bit left.
Plus?
Okay, good. I'll give you the benefit of doubt that we have done it correctly. You know? That what he was whispering you is to put a dot here, you know, product. You know. Okay, so the T actually looking like a plus sign, you know, so the T should be brought down. Okay, is it correct? So this is the voltage division. So V in, this is your equation 5. Okay, so what we wish to do is that replace V out by V in, you know, in terms of V in. So you can write this as V in into R plus Z divided by Z equal to V out, isn't it? This is equation 6. Okay, from the voltage divider expression, I write this one. Is it fine? Am I allowed to do this? Okay. So I just now what I will do, why I did this? I wanted to replace V out by a term which contains V in, you know. So I am going to put it here now. Okay. Use 6 into 4. Then what you have? You have Z in is equal to R into V in divided by V in minus that thing over there. V in R plus Z divided by Z. Okay, V in R plus Z divided by Z. So here we can see that we have V in the top and the bottom. Can you see it? You want to do it? Yeah, come. You finish. It's very easy now. You know, it's coming to a very easy piece of cake. So you can have the cake.
Straw cake.
Yeah, let him have the cake by himself. You know, he doesn't want to share it. you can't cut one of them. You have to cut. You have to remove this. You see, you take this common. This will go. This will go. This will go also. You see, you take all of them. Yeah. Yeah. Okay. So then now write the next step. Okay. You've got your R. You know, do it little bit. There's no rush. You know. Okay. Put the line gradually. Okay. Then you have 1 minus.
1 minus.
Yeah. 1 minus this one. Yeah. R plus Z by Z. Divide by Z. Okay, now simplify this. Have you finished? Just simplify this, you will get the minus Z. Yeah, you simplify this. Whatever you do, you simplify. What is it? You're not writing?
Yeah.
No, you write yourself. Everybody has to write separate.
Have I got this down to right?
Yeah. Just remove the beams from top and bottom. Take common. Yeah, right. No, you just take a common. Okay. It's very simple, you know. You're forgetting your high school algebra. You put R here. Okay. This one. Put Z here. Okay, then put the Z here, then minus R, minus Z. Am I correct? Okay, then you cancel your Z here and here, then you're left with R divided by minus R divided by Z. Got it? So then what you do is that you cancel your R on top and bottom and you are left with minus Z. Okay? So your Z in is minus Z. So I could put this in the final exam. I could, but I don't know whether I would. But it could come, then you should be able to derive it, isn't it? Yeah, Jacob, you should be able to derive it. Okay, you got it? Manually erase it. Just keep on writing. Keep on writing and make sure you understand in your mind, you know, what this is trying to do. Okay? You have to take your time, write it down. Manually erase it. Just write it down. Got it? You know how to get it? How to get it?
No, I need to work for that.
Yeah, walk through it now. Walk through it now. See, I walked through it already, you see? All of this is walked through, you see? This is walked through. You know, cancel this, take this common, then you have get this, then goes this, then goes this. So I can give you a trace, you know? So you go this way, you go this way, you go this way, then you go this way, then you go this way, then you go this way. This, then this, then this, then this. Amelia, you got it? Okay? Anybody who is totally lost? Anybody who is totally lost? What is going on? Are you totally lost? Who is lost? Anybody lost? Nobody is lost. Who is lost? Are you lost?
Yeah, why did you substitute things?
Huh?
Why did you substitute? Is it there?
Yeah, arrow going down showing you which equation after which equation. After this, I did this.
Yeah.
After this, I did this.
Yeah.
After this, I did this.
Yeah,
This one is, you see, this I'm just rationalizing it.
yeah.
Z minus R minus Z.
Yeah.
Okay, and then Z and Z will cancel. And then you will be left with minus R by Z, which is this. And then you cancel R from top and bottom. And you will be left with minus Z. Because it's 1 upon Z here, so it will go up. Okay, have you worked it out? But make sure you do it yourself.
Yeah.
Understanding is one thing, and doing it sometimes is different, not the same thing. Like you understand everything, then you go to the thing you write.
Yeah.
The end. That's why I write in the book. I could also understand everything and show you the PowerPoint.
Yeah.
Yes, I understand everything. I hope you understand everything. Let's go on. See, it doesn't work. It doesn't work. That's why I write down. You have to write it down to understand. Okay, so this is going to convert Z in equal to. So now what we should do is that we take this whole thing and put it in a box, which is called negative impedance converter. It's also sometimes called a gyrator. And it actually has a equivalence in mechanical engineering. This gyrator, this mathematical deduction has a similarity with a gyroscope. You know a gyroscope in mechanical? That gyroscope has some resemblance with the gyrator. So I'm not going to go into that, but I'm going to just tell you that this is called gyrator and it has that resemblance. Okay? So this one I'll put, say you have input here and then here you have a Z, okay? You have a Z here and looking into here what you see? Just put the whole thing in a box. Okay? Simple. Put the whole thing in a box, which is this whole thing, and just keep the Z external and looking in, what is the impedance looking in? What is the impedance looking in? Minus Z. Minus Z? Okay, so this looking in is minus Z. So let us now do an example of a circuit with impedance converter and see what is the end result that you get in. Okay, so I have a circuit here, example. Of negative impedance converter. So this is what I have. You have to tell me what I get. What do I get at Z in at the end? Okay, I'm looking for the Z in, looking into this, and this is a negative impedance converter. Okay, and then from here you have a resistor connected here. Okay, and then this goes to another negative impedance converter. Ni, and this has a resistance R connected to it. Okay, and from the bottom of this R you have a resistance R here, and then you have a Z. So this Z is just a impedance also in ohms. Okay, I put in a box because it is not just a R. It could be R plus L, it could be RLC, it could be L CR, or it could be R and L and just R and C. Any of those. So you have a Z, you have R, you have a negative impedance converter where the R is connected here, R is connected here, and also there is a branch going this way. So the question is, what is Z in?
Negative Z minus R.
Hmm?
Negative Z minus R.
Yeah, you solve it on a paper. See? I always stress that you write it down. So we'll finish this. We'll finish this, then we can go and have our Easter eggs.
Well, we'll cut first. Most of us won't make it to our Easter eggs, we'll be dead.
Okay, what is Z in? Just give me the Z in and this all negative impedance converter. There's two of them. So what you have to do is that looking into here, what you get, put it that up to ground. So if R, what do you see looking here? Negative R, exactly. So you replace this whole thing, put a negative R. And then that negative R will be in parallel with this. Okay, then find a parallel circuit, okay, equivalent, then this R will be in series, find the equivalent value, negative of that is UZ. Okay. Okay, our multitasking people. So find solve the problem, then you can just go back to your single tasking. Combination of negative resistance with this. Okay. Find that parallel value, then
Which would be the secondary equivalence.
okay, so you have here R.
I have that as that one.
So it's better draw every stage, you know.
Yeah, yeah.
It's better. So R, then remove. Draw another one. Remove this. Put minus R. Yeah.
And then you.
Yeah. It's better to draw instead of drawing to conclusion. You know, draw and then go to conclusion instead of immediately drawing conclusion.
So this was what was the non-value?
Ni is negative impedance. From this has to be replaced by what? Negative R? Okay, so this is negative R. So it's always better to do it in stages, you know. So next you do this one. Stage 2, you have negative impedance, okay, and take it out from here. You will R here, okay, and at this point, which is this point you have your negative R, a negative R going to ground, and from here you have got a, put this whole thing in a box, okay, with R and Z, and call it R plus Z. Make your life easier, you know. Put the whole thing, you know. Put this whole thing R and Z together into another bigger box. So put this, take this together and put it in a bigger box. We call it R plus Z. So what is the parallel of minus R and R plus Z? So minus R in parallel with R plus Z equal to minus R into R plus Z divided by minus R plus Z. Okay, just you do use your simple parallel formula. Okay, so this is equal to minus R plus Z. This will cancel, and you have Z in the bottom. Okay, and then what we will do, we will just write somewhere else. We'll write here. Okay, where? Oh, remove the black thing. Yeah, I didn't notice that there's something old sitting here. Okay, so this parallel with this, what will be? You got it?
No. I have negative Z, but I don't know if to try it.
You haven't tried? No.
Yeah, try.
You tried?
It's not right though.
So minus R in parallel with R plus Z is this. Okay. So you put them all together, put the whole thing one piece. Now, so what you have is Ni. You're looking into here, and you have an R here, and then you have put it in another box. You have minus R plus Z divided by Z. Okay. Okay, from here I went here, and then from here I went here. Okay, from here I went here, and then I went here. So R plus this, how much, you know? So R plus minus R. So plus will become minus here, okay? Minus R into R plus Z. Let's put it here, R here, divided by, sorry, R plus minus R plus Z divided by Z. This is equal to how much? R plus this one. Equal to Z here, R here, okay, and this will be minus R square minus, there will be RZ here, okay, minus RZ. Correct?
What happens to the negative in parallel?
Yeah, I have done this here. Negative R in parallel with R plus Z
Yeah. Okay.
equal to, so this is equal to this.
Okay.
Okay, so this now, this thing is here with your R here. Okay, now we have to add the resistance R in series with this resistance. So I am adding R with this series resistance. Okay, so if you add them, then it will be Z in the bottom, and in the top we will have RZ minus R square minus RZ. So this will cancel, and you will be left with minus R square divided by Z. So you can then go into another box where here you have minus R square divided by Z. So how much is Z in? R square by Z. Okay, this is coming in the exam. I don't know, but it could come. So you better practice it at home. You know. It could come in the midterm. I don't know. Okay, so that's all for today, and we'll come back after the break. Okay, and after the break we'll discuss. So this is the end of all op-amps. You know, I'm not going to do any more op-amps. We'll go into some semiconductor devices. You know.